Hello everyone, my name is Isabella West and I'm a first-year master's student in geological engineering working under Dr. Gabriel Walton. I will be presenting on the research that I and my co-authors have conducted on simulating the behavior of compressively loaded Blanco Mera granite using bonded block models. Before I start discussing my research, I'm going to give a brief introduction to bonded block models. So bonded block models, often referred to as BBMs, are a numerical modeling technique that represents a sample of material as a collection of individual grains. You can see an example of a BBM in this image here, where the material sample is the whole rectangle and it is broken up into smaller grains, which are the blocks. The colors of the grains here are just used to distinguish boundaries, so the colors don't have any meaning. The macroscopic behavior of the material sample during a simulation depends on the microscopic behavior of the smaller blocks. BBMs are a type of discrete element modeling method, meaning each of the blocks deform intrinsically based on a set of input parameters. But blocks also interact with adjacent blocks, in which interactions are governed by elastic and strength input parameters. My specific BBM was used to look at stress-strain behavior of numerically modeled rock samples as a potential rock mass analog. One important purpose of studying rock mass behavior is to be able to create safer and more effective excavation design. Understanding how rock masses behave before and after failure is critical for both tunneling applications, in this picture here, as well as surface excavations, like the one here, which was done for a roadway. Engineers want to avoid catastrophic failures, so there is great importance in understanding the stress-strain behavior of the rock mass in which the excavation will take place. Historically, stress-strain behavior of rock masses have been studied in a laboratory, where rock samples are tested in a triaxial apparatus under various confining pressures. However, sample preparation for such tests, as well as conducting the tests themselves, is difficult, labor-intensive, and time-consuming. Therefore, BBMs can be used to simulate these laboratory tests to ameliorate some of these limitations. So first, I built the geometry of my BBM in a program called Neper. This program generates polygonal blocks with specified average diameters and angularities. Specifically, a mean diameter and corresponding standard deviation, as well as a mean angularity and corresponding standard deviation, must be inputted into the program. The diameter inputs were chosen by fitting a normal distribution curve, this green one, to constituent mineral diameter distribution curves, which are the shorter ones down here. These mineral curves correspond to each of the 4 constituent mineral groups within real Blanco Mera granite, so mica, quartz, alkali feldspar, and plagioclase. Each mineral's grain diameter distribution came from data from a petrology report from a past study that tested real Blanco Mera granite in the laboratory. The mean of this overall fitted curve here, plotted in green, is the weighted average of the reported mean mineral diameters. So you can see that the normal fitted distribution that I chose encompasses all large grains of the rock, but it doesn't exactly encompass all small grains. This had to be done because of a limitation within the program that was used to run simulations on the BBM. The program could not run tests when grains of very small diameters were included in the BBM. So a slightly smaller standard deviation was used for this overall curve than was ideal. The angularity inputs were chosen so that the general shape of the blocks in the BBM matched that of real Blanco Mera granite, shown in this image here. After the BBM geometry was built in Neper, the Itasca software UDEC was used to assign grains to mineral groups, which are plagioclase, quartz, alkali feldspar, and mica. So on this image, the block geometries were built in Neper, but the mineral group that each of the blocks are associated with was assigned using UDEC. So this was done with a script that assigned each block, one by one, to a mineral group based on statistical calculations. In simple terms, these calculations result in blocks of large diameters likely being assigned as plagioclase or quartz, since these two minerals have higher mean diameters, And similarly, blocks of smaller diameters will likely be assigned as alkali feldspar or mica, since these two minerals have smaller mean diameters. In addition, my goal was to match the mineral composition of the BBM to that of the real rock. So each mineral group was capped once the reported mineral proportion was reached. Therefore, if a subsequent block would be assigned to a mineral group that has already been capped, the calculation would be redone until the block was assigned to a group that had not yet been capped. This image shows the final BBM after all blocks have been assigned to a mineral group. The final mineral proportions, as well as average diameters for each mineral group, was calculated and compared to that of a real Blanco Mera granite. So based off this table here, you can see that the mineral proportions of the BBM match very closely to those of the real rock. Similarly, the average diameters of the blocks in each mineral group closely match that of the real Blanco Mera granite. The only deviation is for alkali feldspar, where the average block diameter is 0.35 millimeters smaller than that of the real rock. Unfortunately, the average diameters cannot be matched exactly for all mineral groups because of the limitation where a smaller standard deviation of block diameters had to be inputted into Neper when building the BBM geometry in order to allow simulations to actually be run in UDEC. After the blocks were assigned to mineral groups, a calibration process was conducted to match the stress strain behavior of the BBM to that of real Blanco Mera granite. The calibration process included running a series of UCS and triaxial test simulations in UDEC. What is being calibrated here are the input parameters of the blocks, which are the ones I explained in the introduction to BBM slide, where the block deforms intrinsically based on elastic moduli, and blocks also interact with adjacent ones based on contact elastic and strength parameters. Each mineral group has a unique set of block moduli, and each contact type has a unique set of parameters as well. So during the calibration process, a UCS or triaxial test is simulated with a specific set of input parameters, and the stress strain behavior is plotted, like it's shown in this graph here. Rock properties such as elastic moduli, calculated from the elastic region of the plot, as well as peak strength, like here, 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 etc., were observed from these plots and were compared to the corresponding properties of real Blanco Mera granite, which have been previously calculated from laboratory experiments. Input parameters are continued to be varied until all pre-peak properties of the BBM are matched to that of the real rock. Specifically, Young's modulus, Poisson's ratio, peak strengths, and crack initiation and crack damage thresholds were matched to laboratory data. These plots here show peak strength and crack initiation and crack damage thresholds plotted as a function of confinement. The laboratory data is plotted as blue circles, and the corresponding value from the BBM is plotted as a red square. Plots were not made for Young's modulus and Poisson's ratio since these parameters don't change with confinement. So as you can see from these three plots, properties of the BBM plotted within the ranges of laboratory data under all confinements. This project is only in the beginning phases. The BBM still needs to be calibrated to much higher confining stresses, since currently it has only been calibrated to up to 12 megapascals of confinement. However, laboratory tests have not been performed past 14 megapascals, so more laboratory data is required to finish the calibration process. In addition, this BBM has modeled all blocks elastically. However, inelastic blocks are required to match post-peak behavior as well as pre-peak behavior under higher confinements. Inelastic means that the blocks are able to break, so inelastic models more accurately represent real life, where individual mineral grains crack under stress. So my next step will be to restart the calibration process using inelastic blocks. Finally, once the BBM is fully calibrated, pre-existing joints can be added to the model and the stress strain behavior can be compared to jointed laboratory specimens. In general, this process can be extrapolated to other rock types, given that laboratory data on stress strain behavior is available. So BBMs can be used in lieu of laboratory tests to acquire data on the stress strain behavior of rock masses. This data can then be used when designing excavations, where an increased knowledge of rock mass behavior will lead to safer and more effective excavation design. Thank you everyone for your time.